This video is going to cover the eccentric column load design. So this time we're talking eccentrically loaded columns. That means that the load is not at the center of the member, meaning that for our stress, our maximum stress, we technically have axial and we have bending stress. Axial again is P over A and bending is M times C over I. So now we actually have a combination of things, which definitely means it's going to buckle a little bit faster. And to do this, we actually have two different ways we can calculate or really design columns for eccentrically loaded columns. We have what's called the allowable stress method, this one here, where we simply calculate sigma maximum, the maximum amount of stress, and set that equal to the allowable, sigma allowable. And allowable, this guy here, this is from the concentric equations. So the same ones that we used before. This time just sigma that we actually have is not just P over A, it's also including bending. That's the easiest one. It is very, very, very conservative. And in that regards, conservative is nice. It means you have over-designed for it, but it does mean it's a little bit more costly than what it needs to be because you've made a much bigger column than what was required. So it is good, but it might not be best for cost. And so we have another method, and this method is called the interaction formula. And of course, it's also going to be conservative, but not quite as conservative. So for this formula, it boils down to sigma A over sigma A allowable plus sigma B over sigma B allowable. And that has to be less than or equal to 1. And if it's specifically steel columns, then they have another requirement as well, and that is that the allowable for our axial, that little blip, the first part of that equation has to be less than or equal to 0.15. So just an additional piece for steel. So how you get sigma A allowable is, again, the exact same way that you did before, which is concentric equations. How you get sigma B allowable, this guy, is technically from the code book. So for as far as we're concerned, he's going to be given for us. Because our class is not actually focusing on how to read code books and use code books, you're just going to have to understand that it came from a code book, and we're going to give it to you in the problem statement. So again, we have two different methods. The interaction formula is not too terrible, but is a little bit more steps, you might say. It's not that bad, though. It's not that bad. So what we're going to do here in this example is we have an aluminum column. It is fixed free. As you can see, it's free up there at the top. It's fixed there at the bottom. And it is a hollow shape. Yeah, we actually do have a lot of hollow steel shapes as well, but this one's going to be aluminum just because. And this shape is 3 by 6, and it has a thickness of 0.5 around the rim. And of course, P is not at the center. It is 6 inches along in our X direction from the center. And what we want to do on our 8-foot column is we want to find what P is. What is the maximum P? I guess I should say P max. And we're going to do it in two different ways. We're going to do the allowable stress method and the interaction formula so that you can see both of them and get two different answers. So first things first, we're going to be doing the allowable stress, even though they're mostly going to start off with the same steps, right? First things first, if I'm finding P, I do need to know what is my actual. What is my actual? I don't actually know that because I don't know P, but it is P over A. So P, don't know him, just big old dude here in red, very unsure. And area. What is the area of my member? Again, if we just draw this out a little bit clearer, it's 3 tall. Should probably keep my colors the same. It's 3 tall and 6 wide, and then we have an inside shell as well. So if we're going to find area, we need to remove the inside piece. So it's 3 tall and it's 6 wide. if the thickness here is a half, and here is a half, and here is a half, and here is a half, then 3 minus a half and a half is going to be a grand total of 2 inches tall, and 6 minus a half and a half is going to be 5 inches wide. So there we have the outside dimensions and the inside dimensions. So again, I need the area of the ring itself. It's not really a ring, but you get it. It's the rectangular ring. So that area is going to be 6 by 3 minus 2 by 5. And we're going to get that we have P divided by 8. I should probably keep colors consistent here. So 8 inches squared. So okay, that's P. We could write it a little bit better. We could just say that this is 0.125 times P. That'll be nice later on. So there's our first one. That's our actual for our compressive axial stress. Now we need bending. So again, remember that bending is equal to M times C divided by I. Okay, well for bending, we do have to know what direction we are bending about and what our moment is. So again, a moment is simply a force times a perpendicular distance. So our force is P, our distance is 6. So our moment is going to be 6 times P. That's our moment. C, again, we have our, let's pretend our little force, I'll stick him on this side. Our little force is over here for P, and we set our distance from the center out to this part was 6 inches. So that means we're bending about our y-axis, right? This force is going to rotate around our y-axis. So for bending, we need to actually find for our equation the distance from the outside fibers to that axis about which we are bending, which is this much. That is 6 divided by 2. So we have, again, 6 was our dimension, and we're going to divide by 2. Okay, so that's C divided by I. Again, we just said that it was I about the y-axis that we're bending. So again, we need to do 1/12 the base times the height. But again, we are doing the y direction. So the base about the y-axis here, this vertical y-axis, this axis here, the base, that is going to be parallel to that line. So parallel to that line, our base is actually 3. So we have 3 inches times, again, the height is 6 inches then, and cubed. So we're going to get, for this one, I'll put it in purple just so we have something here. You're going to get 0.543 times P. Okay, so now I have my two actuals. Now I need my maximum. Right, so for the allowable stress, we simply find a maximum, and our maximum is just what's our A plus what's our B. So for us, we said that's going to be 0.125 times P, plus we have our 0.543 times P. So grand total for us, what we're going to get, I'll put it in a new color, I guess green. We're going to get 0.668 times P. P's just coming with us. He's along for the ride. So now we have our maximum, and what we need to set it to is our allowable. So what's our allowable stress equation? That's the real question. Well, remember that it is aluminum, so we're going to be looking at our 3 different equations for aluminum. And in order to use those equations, we need to know what KL over R is. Well, the funny thing about this is that we don't necessarily care about which axis we're bending. We're actually just going to be conservative and just use whichever KL over R is greater. So what is K? K is going to be, for a fixed free, K is 2. So we have 2.0 times L. The length of this thing was 8 feet, but we don't really want it in feet, do we? No, because it needs to be unitless, and R is about to not be in feet, so this needs to be 12 inches in a foot divided by R. R here is not very fun. We are going to check both of our R's. So R again is the square root of I divided by A. Huzzah. So we're going to have two different ones for our two different directions. And truly, it doesn't actually matter which one. But here we go. For I, it's going to be the moment of inertia of the outside rectangle minus the inside. So for this one, I'm going to do a base of 6 and a height of 3 cubed minus, again, 1/12 the inside, which then would be 5 and 2 cubed, divided by the area. Again, the area, we actually already found the area up there, 6 times 3 minus 2 times 5, which was 8. So I'm going to just go 8 inches squared here. So for our first value of R, we're going to get 1.127. Okay, I'm going to put that into a nice color. How about we do orange? So we get 1.127. For our second value of R, we're going to go the other direction. And for the other direction, we have 1/12, the base of 3, the height of 6 cubed, minus 1/12, the base of 2, the height of 5 cubed, and then still divided by the area. The area was still 8 inches squared. So cool. So for this one, we get R of 2.036. You might be wondering, which one am I supposed to use? Remember that we want, for our KL over R, we want the larger value. So the larger value for KL over R is going to be actually using the smaller value of R. Don't believe me, you can plug it in. But if I plug in a smaller 1.127 here, if I divide by a smaller number, I'm going to get a larger number. So my value for KL over R, what beautiful color should I do? I'll do pea green, I guess. This lovely pea green color I'm going to get for KL over R is 170.4. What do I do with this information? Well, now I go back and I check my 3 equations for aluminum, because that's what we're made out of, right? We're made out of aluminum. So I'm going to go back and check my 3 equations for aluminum, and I'm going to realize that this is definitely larger than 55, which means we're going to be using equation number 3. And equation number 3, which you might not remember, it's just absolutely fine. Equation number 3 was sigma allowable is equal to 54,000 divided by KL over R squared. Okay, and we just calculated value for that. So our sigma allowable, again, 54,000 divided by, we said KL over R was 170.4, and we're going to then square that value, and we're going to get a sigma allowable of 1.86 KSI. Okay, so now what do I do with that information? Well, we have a sigma maximum right here, our 0.668p, and we have an allowable, and we set those two equal to each other. So we said we had 0.668 times p, and we're going to set that equal to our allowable, which was 1.86 KSI. Now, technically, I should have been a good person and kept up with my units the whole way, but you're noticing that we have inches divided by inches to the 4, so yep, that's going to be technically in whatever p is divided by inches squared. And as you can see, that one's definitely in 1 over inches squared as well. P divided by 8 inches squared, so therefore this is going to be in 1 over inches squared. So keeping up with my units and paying attention to that, if this is in 1 per inches squared times p, and the other side's in KSI, then p is going to be given to us in kips. So therefore, for p, we're going to get 2.78 kips. Okay, yay. Not really that surprising that this very, very skinny little rectangle of 8 feet tall can't really hold that much. 2.78 kips might not seem like that much because 2 is a really tiny number, but I mean, it is 2,780 pounds, and that's pretty significant. So again, that's just using our allowable stress method. But again, we also said we have the interaction formula. So now let's do it with the interaction formula. And to use the interaction formula, we're going to kind of separate some things out. Remember that the interaction formula, we have sigma A, our actual, divided by sigma A, allowable, plus sigma B, our actual, divided by sigma B, our allowable. And that has to be less than or equal to 1. Because this is aluminum, we don't have to do the additional check. But we do have to solve for those things individually. Now, conveniently, you've actually already solved for this, you've already solved for this, and you actually already solved for that as well. So really, the only thing you need is this guy. And that guy is usually given, we said, so let's just say that we're going to give this value, sigma B allow, is going to be, let's say, 5 KSI. How does that change things? If we only have an allowable bending stress of 5 KSI, what is P? So let's go back up and find what our things were. We said for actual, for our axial, is 0.125 P. So we had that in a blue color. So we had 0.125 times P for our sigma A, divided by the allowable, which again, because this is based on KL over R, and K is definitely the same, L is the same, R again is just properties of the cross-section, that hasn't changed. So yes, even our equation 3 here that we found, 54,000 divided by KL over R squared, that has nothing to really do with our given loads, right? So that is still going to be 1.86 KSI. So we're dividing by 1.86 KSI. Don't forget that this dude is in 1 over inches squared. And then we're going to add sigma B. So sigma B, good thing we separated these, right? It's apparently purple also, 0.543 times P. So we had 0.543 times P, and again, he is in 1 over inches squared, divided by our allowable, and I just made that number up, honestly, so it's 5 KSI, and we want this to be less than or equal to 1. Now, technically, if you were having to do a design, the interaction formula could technically be quicker than trying to plug and chug into all of that stuff for your interaction equations, especially if you have like a W shape. So you kind of just pick one and try it out, and you just see if you're checking that this stuff is all less than or equal to 1. The closer you get to 1 without going over, the better your choice actually was. But it, for us, we're just calculating maximum P, so that's not our case. But again, the closer you get to 1 without going over, the better. So now I'm actually going to solve for this, so I'll put it in, I guess, a green color. Be nice. And I'm going to get, obviously, something times P plus something times P, and that's technically 0.067 times P, plus, and the other one we have 0.1086 times P, and all that needs to be less than or equal to 1. So you add it all up, and you get 0.1756 times P, who's less than or equal to 1. Solve for P, and we get that P is equal to 5.69 kips. And you might be thinking, wow, the difference between these two numbers, 2.78 and 5.69, that's like almost double. And yeah, that's pretty much basically a function of that guy right there, right? If he was a bit bigger, then obviously this would change things. But either way, again, the interaction formula is still conservative. It's just not as conservative. So yes, depending on how the question wants you to do it, you will get two completely different answers. So do be careful with that. But really, there's two different ways to do it. They're not too incredibly different. They're not really that different. You're still solving practically the same amount of information. Just at one point, we add them all together, and the other point, you keep them separate, and you just have a different allowable thing. That's it. So hopefully you don't actually find this eccentrically loaded columns to be too incredibly difficult.